Azure Disk Encryption provides a robust method for securing data at rest on both Windows and Linux virtual machines. By leveraging Azure Key Vault, administrators can store and manage encryption keys using enterprise-grade security. This encryption process integrates tightly with Azure Resource Manager, ARM, templates, or bicep files, ensuring encryption settings can be automated and consistently deployed. From earlier topics on templated deployments, we carry over the principle of defining repeatable configurations, adding an extra layer of protection through disk encryption. Properly configuring this feature helps organizations meet compliance targets, maintain data confidentiality, and reduce instances of unauthorized access within their cloud environments. Implementing Azure Disk Encryption requires setting up an Azure Key Vault to manage encryption keys and secrets securely. Administrators create a dedicated vault or reuse an existing one, ensuring it meets compliance standards. Next, they must configure access policies to allow relevant Azure services, such as the Azure Virtual Machine or Azure Disk Encryption Service, to retrieve these keys. In many scenarios, an Azure Active Directory, Azure AD application is used to authenticate requests. By tailoring access policies precisely, organizations reduce the attack surface, only granting the minimal set of permissions needed for both operations and maintenance within the environment. Administrators can enable Azure Disk Encryption by extending existing ARM templates. In JSON-based ARM files, add a resource definition referencing the Azure Key Vault and specify the encryption settings for the virtual machine. For instance, under the virtual machine resource, include the encryption extension resource referencing the Key Vault ID and the required version of the public settings. This integration streamlines deployments by automating the encryption process as part of a standard provisioning workflow. By doing so, environments maintain consistent security configurations, benefiting from earlier template-based deployment best practices, while safeguarding sensitive data through encryption and secure key management. Similar to ARM templates, Bicep simplifies the configuration needed to enable Azure Disk Encryption. Administrators define parameters for Key Vault information, encryption settings, and extension versions. Bicep's cleaner syntax makes the encryption extension declaration more compact, while preserving all essential properties. Once deployed, the Bicep file translates to standard ARM constructs, guaranteeing compatibility with existing pipelines or policy definitions. This approach allows organizations familiar with Bicep to integrate disk encryption into continuous integration and continuous delivery processes. Consequently, teams maintain alignment with DevOps practices and all encryption-related settings remain version-controlled, enabling quick rollbacks or version updates as requirements evolve. For instances where Azure Disk Encryption requires direct interaction with the Azure Key Vault, an Azure Active Directory application may be necessary. Through the Azure portal or command line options, administrators register an application and assign it the appropriate rights. Within Key Vault, administrators grant the service principal permissions for key and secret operations. This step is crucial for automating encryption tasks, especially at scale, as it allows scripts and templates to authenticate without manual intervention. By adopting the principle of least privilege, administrators reduce exposure of these credentials, ensuring the application's access is limited to essential encryption operations only. Azure Disk Encryption for Linux VMs leverages the BitLocker-based mechanism on OS disks and dmcrypt on data disks. After linking the Azure Key Vault, administrators enable the encryption extension, which installs required packages on the Linux operating system. Scripts handle key generation and secure storage, ensuring the OS reboots only after verifying access to the cryptographic material. This process may involve minor downtime, so scheduling windows is often recommended. Monitoring the extension status becomes crucial, as any misconfiguration in vault permissions or pre-existing dependencies can slow the encryption process. Proper planning ensures minimal disruption and maintains secure, reliable workloads. For Windows VMs, Azure Disk Encryption relies on the BitLocker feature to secure OS and data disks. Once the virtual machine extension is installed, It communicates with Azure Key Vault to retrieve the encryption key. Administrators should confirm that BitLocker is enabled and functioning. While encryption is in progress, system performance may temporarily degrade, and scheduled tasks should be managed accordingly. Once complete, the VM reboots to activate the encryption, storing the key in the vault. By combining Windows-specific security safeguards with Azure's key management, organizations gain a uniform approach to data protection across heterogeneous environments. Successful Azure disk encryption hinges on meticulous planning. Administrators should ensure the key vault is set to the correct region. Monitor permission assignments regularly. Employ separate vaults for production and testing. Validate encryption extension versions for compatibility. Maintain consistent naming conventions across resources. By adopting these practices, teams preserve a clean environment and enable rapid troubleshooting if unexpected behavior emerges. Automation through ARM or Bicep templates fosters repeatability and lowers misconfiguration risk. In all scenarios, thoroughly testing encryption and decryption processes in non-production environments helps confirm that data remains secure and accessible once deployed. Monitoring ensures that disk encryption processes complete successfully and remain compliant. Administrators can track extension deployment statuses via Azure Monitor or Log Analytics workspaces. By enabling diagnostic logs on the Key Vault, they observe key retrieval activities and identify suspicious usage patterns. Auditing offers an additional layer of insight, preserving records of access attempts and configuration changes. For instance, if an unauthorized role assignment is detected, administrators can revoke it to preserve the environment's integrity. Combined with proper alerts, monitoring and auditing form a proactive defense mechanism, enabling organizations to respond swiftly to anomalous requested actions and potential breaches. When encrypting multiple virtual machines simultaneously, consistency in encryption settings becomes paramount. A recommended approach is to define shared parameters in ARM or Bicep files, then loop through machine resources. However, large-scale encryption efforts can place additional load on the key vault and impact performance. Administrators should consider staggering deployments, employing capacity planning, and leveraging scripting for batch updates. Creating dedicated vaults per region or workload can enhance reliability while still adhering to centralized governance policies. By fine-tuning the encryption approach, organizations maintain efficient resource usage, uphold security compliance, and meet business requirements for operational continuity within Azure.